Hi, I'm Kyle Finner. I'm a staff scientist here at IPAC, and we have 5 talks this morning. One is invited, and the first invited talk here is from Anna Bonaca from Carnegie Science, and Anna will be talking about stellar streams with the Roman Space Telescope. Go ahead.
Thank you.
I meant to be on TV. I think there's the TV. Okay. So I want to start this talk with this beautiful image of the antenna galaxies because they illustrate the underlying physical principle of what stellar streams are. So they are tidal debris of interacting galaxies or interacting galaxies in globular clusters. So that's one reason. The second reason is because it is somewhat historical example, very local one, of what physical understanding we can gain from large catalogs of galaxies. So I'll accept this one. Right. So the antenna galaxies are really only one of 388 galaxies in the ARP catalog. So I'm showing the images here that were first published in 1966. The mice, the antennae, an unnamed pair that's only known by its ARP number, 295. And what has been interesting is the origin of these galaxies was actually demonstrated a few years later by by Tumre and Tumre in the seminal paper in 1972, where they ran very idealized simulations of tracer particles interacting in a potential of 2-point masses to reproduce almost exact morphologies of these systems. So these are, I think, pretty good. This may be a little bit misaligned, but I feel like for 2-point masses, this is a great success. So this has been one of the first demonstrations that galaxies interact and can grow through merging with other galaxies. And this was the prediction at the time of the kind of nascent cold dark matter universe paradigm. And to this day, the stellar streams and this tidal debris kind of remains this irrefutable evidence that galaxies and structures grow through hierarchically through merging. However, what we want to understand now is has a little bit shifted to smaller scales. So the question we want to answer now is what is the particle nature of dark matter? And here I'm showing 3 models that were started with the same initial conditions in the early universe, but assuming different dark matter physics. So the vanilla, the standard cold dark matter model is here on the right. In the middle, we have self-interacting dark matter model that is pretty similar to cold dark matter, so massive particles, but in this case, they are interacting through forces other than gravity. And then finally, a warm dark matter model on the left, which is similar to cold dark matter, just with lighter particles. And so you can immediately see on this Milky Way mass scale halo, there are some differences. So the centers of galaxies have different shapes. Kind of the SIDM is the most spherical, then CDM is more triaxial, and then the warm dark matter can be even more elongated. And there is also the difference in the amount of substructure that these models predict and its properties as well. So the warm dark matter, because the particles are so low mass and can kind of free stream out of these low mass clumps, has noticeably fewer substructures and fewer satellite galaxies expected than, for example, cold dark matter and self-interacting dark matter, which have a similar amount of substructure, but very different density profiles. So you can see in the CDM case that we have roughly similar density profiles and similar concentrations, whereas in SIDM we have almost a dichotomy. We have some very diffuse substructures and then some very compact. So what we'd ideally like to do, and has become sort of an industry in the last 20 years or so, was to use some tracers in stellar halos of galaxies to trace the gravitational potential and determine which of these models is the one that we live in. So Luckily, in the Milky Way, we now have more than 100 such tracers. And so I'm showing here a map of actually published members of identified stellar streams compiled through the literature. A lot of them are coming from the Gaia satellite, but there are some from photometric projects like mostly DS at this point, but some Pansars and some other asteroids as well. And so, okay, let's walk through first. On the right, we have the zoomed out image that shows the entire map, and then on the right, there is a zoom in onto the Milky Way disk. The location of the sun is marked with a star, and then you see this disk plane and different distances, kind of the 12 kiloparsec would be sort of the extent of the disk. You can see that there is a lot of streams detected overall. Most of them are close to the sun, which makes sense. It's possibly largely a selection effect. The color coding here is by the orbital orientation of these stellar streams. So as they go around the galaxies, those that are marked in orange and red colors are moving in the same direction as the Milky Way disk stars do, and those in the blue colors are moving or orbiting in the opposite direction. So you can see that they both span different locations in the galaxy now, and also in the past they were exploring different parts of the galaxy as well. So in this sense, they are sort of ideal tracers of this outskirts of the galaxy. And in particular, in this talk, I'll be focusing on these very thin stellar streams, which we think all originate from disrupted globular clusters, rather than dwarf galaxies like this most massive one, the Sagittarius dwarf galaxy stream here. Okay, so how do we use them to map dark matter? So I'll give two examples for mapping the large-scale structure or the halo shapes of dark matter, and then, yeah, large scale means here still within a single halo or within a galaxy. And then the second example will be on the substructure. So there has been a lot of, more work along these lines in the last couple of decades, but I will show here a method developed by Jake Neubauer, who is a student who just graduated from Princeton and is moving to Harvard in the fall. And like this method was developed sort of as a something that, or based on something that we learn in kind of physics 101. Which states that if we know gravitational potential and we know the initial position and velocity of an object, we can calculate its trajectory or its position at any point in time. So kind of schematically, we're writing this down as 6D position, some potential, we can get the position at another time, this I+1 index. And this is kind of how all of the simulations that Phil and others talked about work these days. We have some very small time steps, and we are evaluating where stars or star particles or other types of particles are moving in the simulations. And so what Jake realized is that he can invert this and say that in streams, we kind of know where the next particle moves, so the stars in the streams are moving one after along the other. And so from that, we have still these two properties of the above equation. We have the positions one after the other, and can use that to back out what the acceleration field should be along that trajectory. And so this idea is very simple and works with like kind of in the physics lab when we have, we can precisely measure the position and velocity for stellar streams. It's a little bit harder. So it took a while to compile the data set that this can be applied to. But then last year, Jake realized that we have such a data set for the so-called GD1 stellar stream. So I'm showing here just two components, so sky positions and then the radial velocity gradient. And so then what he did was trace these trajectories and calculate which acceleration field in this kind of individual grid points along this basically spline fit are consistent with the data. And to get cut to the chase, so here are his measured acceleration vectors in the xy plane. So this is the plane of the disk. So you can see we are, with this one streams, probing only a small part of the galaxy, but you can still find some interesting results, and that is namely that the halo seems to be triaxial and tilted with respect to the disk. And even more interestingly, when we overplot the shape of the stellar halo measured by Jesse a few years earlier, we seem to find the same tilt and the same halo shape. And however, this is only one mode. There's an equally likely solution for GD1 that looks like this, that is not in agreement with the stellar halo. And currently, just from the dynamics of GD1, we can't tell. But if we had streams in other parts of the galaxies, you can see that we actually could distinguish these models. So this is kind of the name of the game. What we would really like to do is have more stellar streams to apply this to, this type of data, and also in different parts of the galaxy. Okay. Another kind of more direct probe of the small scale structure would come through interactions of stellar streams with dark matter subhalos. So here is a prediction very early on from Catherine Johnson's group, Yoon et al. In 2011, showing simulations of the Palomar 5 tidal tails in different realizations of cold dark matter. And each of them had had an encounter with a dark matter subhalo that is marked with a cross. So these are all different realizations. And you can see that each of these crosses is sort of associated with a gap or sometimes a fold like this in stellar streams. So this is kind of what has been theoretically predicted for a while now, almost, first papers more than 20 years ago. And it took, again, some time for the data to catch up, but now we have numerous examples of exactly these kinds of features. So these are all the GD1 stream that we saw before. Another stream called JLM, Palomar 5 tidal tails, Atlas Alikauma. This is a very interesting example. We thought that originally these were two different streams, but it turns out that they are on the same orbit. So when people measure velocities, you could see that this is actually, where is this? Okay, that this is actually, looks like a broken stream rather than two separate streams. And finally, the last example here is the jet stream, which is particularly interesting because it is much farther away than any of these other streams that are between kind of 10 kiloparsecs and 20 kiloparsecs, whereas jet is at 30 kpc. And so these, what these data enabled is very detailed modeling, and that was only possible because the majority of the contamination of the Milky Way stars has been removed. So for GD1 stream, we found that this sort of feature, the gap and the spur associated with it, can be reproduced. So the data is on top, and the model is here below. Can be reproduced by an impact of a 5 million solar mass object. However, what is unusual is that it seemed to have been a fairly compact object. So it would be sort of a 3 sigma outlier from the 3 sigma overdense subhalo compared to what we expect in CDM. There's been some follow-up work to show that an SIDM halo could reach actually this type of density. So that is one tentative finding for GD1. This is kind of hard work, so there has been really only one other stream for which we have performed such analysis, and this is this Atlas Alikauma, so from paper from Tariq Hilmi a couple of years ago, where they found, so the data is shown with error bars. You can see that they explode for radial velocities and proper motions specifically. However, just from the sky positions, you can get a model to reproduce that if a stream interacted with a 10 to the 7 solar mass cold dark matter subhalo. And so this is a very interesting regime. Below kind of 10 to the 7 is where we expect the subhalos to be truly dark. So if we actually find them, it will be a very strong evidence towards cold dark matter type models. However, what has been hard is that, as I mentioned, these streams are pretty nearby to the disk of the galaxy, so there is still perhaps some possibility that these features were causing interactions with the bar or the spiral arms or the giant molecular clouds. So what we'd really like to do is go further out, and that is hard because stars get faint. So here is an example of jet stream, and it's analysis from the dark energy camera in Delft survey that selected stars in the color magnitude diagram here, and the G versus G minus R is shown. So they basically go to something like 23rd magnitude, and the stream, definitely shows up, but it's kind of hard to say what the density structure in detail is. We can do better. So here is imaging with a megacam on Magellan, where we go much deeper and get more stars in GNR. When we add the U-band for the metallicity sensitivity, we can even further increase the contrast along the stream. So you can definitely see that some of these structures remain, and we do not seem to be able to produce them in a smooth model. However, you can see that our selection, especially here in the G and R colors, is not as deep as we might want to go. And this is because we have a problem, and those are the unresolved galaxies that are starting to creep in. So that's why we cut this short. We're hoping to improve upon this. And very soon, so I was very excited to read that this proposal was accepted in Roman Cycle 1. So the slide is courtesy to the PI, Bill Chen, who is a graduating student from University of Michigan and moving to the Ohio State as a fellow. So what Bill will do is analyze the high latitude wide area survey and search for tidal debris around known globular clusters there. The one that they'll be focusing on first is Palomar 3, which is very distant. And this will be an ideal case. We'll want to detect all of the faint stars, perform the morphological star-galaxy separation, and just see how much better we do, and if we actually can reveal the tidal tails at 100 kiloparsecs, which is the distance to Paltry, and then see how well we can resolve the density structure of the stream. So what he is planning to do is first not even look for evidence of substructure, but just look at what the sort of intrinsic structure of the stream would look like just based on how stars are escaping the cluster. We expect some density variations that are very regular and whose position depends on where the tidal radius of the cluster is, which in turn depends on the enclosed mass of the galaxy at that location. And so what he is showing here in this figure is that based on how separated these peaks are, we can estimate the enclosed mass to 10%. And this is true even in kind of shallower data, but it's more uncertain. But we believe this will be what will be possible to do with this data set. Another interesting avenue for stellar streams has recently been published based on Euclid data. So there has been a number of streams detected in collaboration with the Zooniverse project in the quick release 63 square degree Euclid dataset. So here is 9. They analyzed a sample of 10 ultimately. And what they did, or asked the volunteers to do, is trace these substructures. I'm showing here an example of one annotated in the central galaxy. And use basically just this reduced information to determine statistically the shapes of dark matter halos. So interestingly, they're finding slight evidence for flattening. At this point, it's only 10 galaxies. And here is this is the kind of spherical halo would be at this Q flattening parameter of 1. You can see there's a slight offset away from it, but that is pretty close and could be just due to the presence of the disks. Thank you. What we can expect from Roban, just out of the surveys that are already planned, is expanding this to a much larger number of galaxies. And then you can imagine doing all sorts of interesting things, like binning this in various galaxy properties and see if there are any correlations with halo shapes that are expected from the cosmological simulations along the lines that we saw, that more spherical, probably SIDM, or triaxial, probably cold dark matter. Okay. And then in the final 5 minutes or so, I wanted to get back to kind of what we can expect in the Milky Way. I had the title from dozens to thousands. I think reaching thousands will, with extragalactic streams, will be very possible due to the just area of Roman. But it turns out that we might be getting close to that number in the Milky Way as well. And so a couple of years ago, in collaboration with Sarah Pearson and Bill Chen and Oleg Nedin, we had a forecast of how many globular clusters have dissolved in the Milky Way overall. So we built this model on the merger tree of simulated hydro simulations of Milky Way mass galaxies and TNG 50. They were selected to be Milky Way-like based on the total halo mass, but also based on the merger history. So they had something like the last major merger around 10 billion years ago, and then pretty quiet merger history. And then empirically walked that merger tree to trigger formation of star clusters, assign them to simulation particles, and then calculate what their mass loss from the cluster would be on their orbits within the simulation, and then estimate, when they actually fully dissolve. And we got a sample of more than 10,000. So we went to cluster masses down to 10 to the 4 solar masses. So this is already in the kind of regime of on the boundary of the open and the globular clusters. So there's been a huge compute to get to that number. And here I'm showing this tidal debris organized along 2 axes. So on the x-axis, we have sort of the median sky position of the debris, and on the y-axis is sort of the diskiness, which is the fraction of the angular momentum that is aligned with the angular momentum of the disk. As you can see that, some of these you would say, oh yeah, they look like streams here in the bottom right corner. On the left, we have some very compact things. Turns out that many clusters are dissolved in the bulge. And then some on the top seem to be kind of following the shape of the disk. So excluding those, we get rid of most of the sample. But still, if we make a selection here of these really stream-like things, we remain a sample of 1,000 that we expect in Milky Way-like galaxies. So here is their radial distribution. Most of them still are expected to be closer into the galaxy, but a number are within or outside of the disk, which is, say, 15 kiloparsecs. And of the known Milky Way streams, most of them actually are within 20 kiloparsecs. So we really are not seeing any on this purely dark matter-dominated region. And we made the initial forecast here assuming LSST Rubin photometry. So here I'm showing kind of where they are on the sky if we assume that we have a magnitude limit of G of 27. So you can see immediately the problem with Rubin being a ground-based. We'd really like to have this full sky image to get the entire sample. Another problem that we alluded to before is that to really get to the G of 27, we need to have a morphological star-galaxy separation. So if I were to write to Santa, it would be something like, please, a Roman all-sky survey would be great for cell streams. We actually could discover every dissolved star cluster in the Milky Way halo. So with that, I'll take questions. Thank you.
Questions? Go ahead.
Hi, Anna. Very exciting. I do know you're involved with ViaSpec. How is that going to be incorporated into, or will it, with the spectroscopic follow-up?
Sorry, did you say?
ViaSpec.
Oh, ViaSpec.
Yes, and whether or not, what role that will have with the science cases you've outlined here.
Yeah, that's a very good question. We some methods or some aspects here really rely heavily on having spectroscopy for the halo shapes. It's nice to have the radial velocity gradient. Even for the substructure, so this is, which will be the main thrust of VIA. I will show it on this figure. So here is relative radial velocity from unperturbed stream, kind of what is expected for this particular simulation. And you can see it's on the order of a few kilometers per second, that there should be signatures. They are the data quality now is nowhere near enough that. ViaSpec will go down to 100 meters per second on the, or a few hundred meters per second for the more metal poor stars at the faint end of the Gaia limit, so the 21st magnitude. And our goal is to search for these characteristic features that are signatures of impulsive impact or a flyby of a massive object. So our plan will be to look at the streams that look perturbed in imaging. So in that case, having something like Roman actually clean up that image will be very important. Because and use the spectroscopy to sort of confirm that these features kind of are consistent within the sky, kind of how the sky positions of the stream are perturbed, and that the velocities are also consistent with this scenario. Excitingly, I didn't talk about this arrow point here. But potentially this could actually allow us to constrain the orbit of the perturber and predict where the object should be today. So that would be another exciting avenue for kind of multi-messenger studies of substructure, we get there.
All right, yeah, go ahead. You can go next.
Do streams survive a passage through the disk of the Milky Way?
Some do, many not. So Pal 5 is actually a famous example. I think so, yeah, this is the first globular cluster discovered to have tidal tails and in early 2000s. And then first modeling showed that like this cluster is basically sort of on its last legs. It's very overfilling its tidal radius, and it actually does cross to the disk at a distance of like 7 kiloparsecs, so pretty close. And we think streams like GD1 are much more long-lived. So they're, first, Pal 5 is also a prograde stream, so orbiting in the same direction as the disk. Well, GD1 is retrograde and also crossing the disk at 12 kiloparsecs. So there is, certainly a concern that some of these structures in Pal 5 actually could be caused by the disk, and then the streams on those kinds of orbits are more short-lived. And definitely in our forecast, we see a lot that are just immediately kind of dispersed by the disk. Yeah.
Tiffany?
We have one online question from Marty Glassman. Could stream detection in particular cases help to increase confidence in detection of low luminosity, high Z galaxies if the stream was pointing towards a galaxy in question?
So is the question for extragalactic streams if we have something that is kind of pointing directly towards us? Okay. Yeah, that is, I feel like if it's exactly pointing to us, it's really hard. And actually, we had cases in the Milky Way as well, that there seem to be dwarf galaxies that have long tidal tails, but are sort of so far away, so they're kind of radial towards us, and we haven't been until recently able to determine until we were able to measure distances. So I feel like if that's the case, I suspect that measuring kind of 3D positions within like other galaxies will be hard. But if it's just a little bit not radial, that there is like some extent, then yeah, I can definitely see Roman, especially for the nearby enough galaxies where you can resolve individual stars to be able to see that. Yeah, and potentially even if it's, yeah, this is great and strong enough to actually see the spread in of the RGB.
Okay, thank you. That's all the time we have for questions. Let's thank Anna one more time.